Hello and welcome to the IEEE Spectrum Online presentation, Automated Design Testing Procedures Using Software Simulation Tools. I'm Dexter Johnson and I'll be moderating this presentation. Before we start our presentation, I would like to mention a few housekeeping items for those of you who want to know if this session will be archived. The answer is yes, it will be archived and will be available for review within about 24 hours and can be found on www.spectrum.ieee.org/webinar. Once the archived webinar is available, a notification email will be sent to all the registrants. Secondly, we encourage questions, and I hope we have time for several, which we'll take at the end of our presentation. But as your questions occur, please type them in the box provided on your computer screen on the left-hand side and hit the Submit button. You don't have to wait until the end of the presentation to begin submitting questions. As you look over your screen, you should also see buttons that allow you to enlarge the slides if you so desire. About volume control. If you are listening to the audio portion of this event over your computer speakers and you need to adjust the volume, turn your attention to the speaker icon at the top left of the screen. You may also need to adjust the master volume of your computer system. At the bottom of the slide in front of you are a couple of additional suggestions that will improve your viewing experience, including a resource page with today's presentation. Now I'd like to introduce our presenter. Dr. Doug Cragen is the team leader of the Benchmark and Testing Group at Integrative. He has a Bachelor in Science as a physics major from the University of British Columbia and a Master's in Science and PhD in Semiconductor Physics from the University of Waterloo. And with that, I'll turn it over to you, Doug, if you'd like to begin.
Hello and welcome to our webinar on automated design testing procedures using software simulation tools. In this webinar, I'll be talking about how to use tools such as Integratives more efficiently, and particularly how to use them to reduce interactive time. Simulation has been well established as a way to do faster and less expensive product design, as well as it serving many other purposes in science and engineering. However, it tends to produce good design insight, and it also reduces the number of prototypes that are needed for testing. The process of running a program can be very time intensive, and simulation tends to produce a lot of repetitive and tedious variants of the same thing. This is slow, it tends to be prone to user error, and it's very expensive in terms of the person hours of work involved. That is, if somebody is sitting there interactively doing very similar tasks over and over, you're paying their time, which could be spent doing other things. Some examples of this are changing of the sizes and shapes and positions of parts that might be in a simulation, applying various voltages, testing out different materials, and doing something like randomized tolerance testing, seeing how much effect small variations in the manufacturing might actually have. All of these are repetitive things, and the computer should be able to run them in an automated way for you. Some other problems that come up in design include that simulation tools might only be accessible to a few trained people. You have many people who could benefit from simulation, but it's not worth the time that will be involved in them training up to use it. Your trained users might also be irregular. It's very common that people using our software, for example, are actually mechanical engineers who spend most of their time doing issues such as size and position and mechanical deformation, and only for short periods at a time come back to the electromagnetic part. And the question is, how much retraining and reorientation do they need when they come back to a software that might not even be in their main line of expertise? So automating the simulation can reduce these kinds of problems. And in this presentation, we will illustrate two methods, parametrics and scripting. The parametrics are a reference to using built-in methods for automating variance in design. And scripting is the ability to write your own code that will make use of the simulation tool, but will enable you to take direct control over the functions in it. So the scripting enables you to do more advanced things because you're more in control, but it is going to require more setup time. So parametrics are easy to set up and use if you're a regular user of the software. But of course, if you're not a regular user of software, then most aspects of it will be very mysterious when you first look at it. Whereas if it's someone who is an expert sets up a script to perform a task, anybody can run the script without having to know that software. You can, with scripting, enable a much larger group of people to be able to benefit from a program. So we'll consider an example of parametrics. In this example, we have a block with a shallow hole. Well, this is very easy conceptually. There are a number of parameters to it. There is the length of the block, the width, the thickness. There's the center of the hole position, the radius of the hole, the depth of the hole, and the material. And in an actual model, it will be combined with other parts, so it will have some absolute position and orientation in an overall model. So if one is going to study this problem parametrically, then you will need to have some way of looping through variations that you want to study. And this setup that's shown is going to study two different things. It's going to shift the bottom surface, and it's also going to move the hole. So we're going to study different thicknesses of the block, and we're going to study different positions of the hole. And when we do that, we're going to automatically pull information out as well. So looking at the interface here, you can see a reference to the parametrics that exist. You can see them shown visually in a looping fashion, and you can see what things have been asked for to be automatically produced. So the field value at a point is going to be queried, and the streamlines coming off of a surface are also going to be studied. So when the parametric is run, it produces a data set for 8 hole depths and for 4 hole positions for this given parametric. The outputs that were predefined can now be used for different purposes, such as to create the plot that you see here, where you can see what the magnitude of the electric field is at the chosen point for different positions of the hole and for each of the depths of the hole. For the more graphical part, which was the generation of streamlines, you can also see something now, which is the shape of the electric streamlines versus the position of the bottom surface. So as the bottom surface moves up, the streamlines are getting shorter and shorter and also getting more intense. So you can see the variations for different positions of the hole and different thicknesses of the block. And as you can see, the animation was simply a Windows AVI file, so you can reuse it in many different settings. The parametrics were very straightforward to set up and to run. However, the constraints that are required by the very nature of parametrics don't necessarily allow you to run all the variations that you want to run. And furthermore, when there's a large number of parameters to be studied, all permutations might be an extremely large number of computations to do. So these may not be necessary, and certainly when you are working live with the program, you have very naturally used what you learned so far to make intelligent decisions about what else you wanted to study. So the nature of parametrics will mean that you tend to do more analyses than you necessarily have to a lot of the time. And also, since parametrics requires knowing how to run the software, they're not useful to many people who might otherwise benefit from simulation. Now, if we show this live, just to give a better sense of it, here is a very simple example of two plates with a voltage on each plate and a dielectric rod in the middle. So if you look at it and you see the electric field plot that is produced, you can see that the field is, of course, reasonably uniform in between the two plates, but there's fringing effects, and there's a very high field at the corner, so a user range was selected to prevent that from swamping the whole presentation. But you also see some bending and color changes around the rod itself. And a very simple but common sort of thing that people will want to study is the effect of things like dielectrics when you change their sizes and their positions within a model. So let's just set up a parametric live here and run it for this example. We're going to go to the parametric setup dialog, and we're going to create a parameter which will be a displacement, so I'll call it move rod, and I'll select the geometry to move, and then I'll specify some number of steps, such as 10. So I've got the rod selected. The next thing is to specify what the movement is going to be. And what I'm going to do is move it to the left, and that's the negative y direction as seen here, by a distance of minus 0.3. So I click apply and I see a parameter created, and so long as this parameter is selected, I see the rod showing up as green. Now if I want to visually confirm what I've just set up, I can go to a validation routine and click OK, and I see there's the various positions that are going to be studied. So that looks good to me. The next thing to consider is what am I automatically going to produce? So if I'm going to study all these positions, there are probably things that I'm interested in. And the first one is I'm just going to produce the same plot as what I just showed. So with the same settings on the field analysis result dialog, I click new plot, and then I'm going to tab to show a grid and select corner points similar to what I had previously. So here to here to here, and we now see that there is a plot defined that's going to appear. So I've now specified one output. Another obvious type of output for a lot of cases will be something like mechanical force. So you see now I've got my mechanical force on volume. Again, note the indication by the green coloring and the solid arrows on a plane. So we'll consider that sufficient for our purposes now. I'll close the dialogues and turn off the grid that's showing up. We'll save the setup file. Now for the arrow plot, what I would also like is to have an animation created. So I'm going to go in and check a box on the menu, which you see now says Create Animation. So when I actually run the parametric now, I'm going to specify that I want the answer to go into something called result. And we can now watch it proceed. And this is a very simple model. That's why I chose something like this for live demonstration purposes. You can see the program itself stepped through all of those variations much faster than I could have manually said move the rod to all of those positions. And now I have my data table, which lets me create plots such as force magnitude versus position. So now I have a plot which it says as I move the rod, the force is getting smaller and smaller. And if I turn on auxiliary axes, I can verify the displacement in terms of how far it's moved according to the X, Y, and Z locations. I can also pull up the animation that was created, so we have our arrow plot. When I click play, I see Windows Media Player open up, and now I can sit and watch the program run through the animation. So let's close the Coulomb program and consider what is more work to set up than what you just saw was very simple, but which does give you a lot more power, and that is scripting. Scripting is the ability to set up a list of commands that you can use to control software. So by running a sequence of commands, you can get the software to perform arbitrary tasks. And if you have a sufficiently sophisticated scripting environment, you can program very effectively what you would like to be done. So there's generally two ways that scripting environments might be set up. One way is internally, and that is to make a scripting language that runs from within the software. So this looks very nicely self-contained and makes the software appear very powerful in and of itself. The other way of doing it is external scripting. With an external script, such as from Excel, MATLAB, Mathematica, SolidWorks, or programs you write yourself with Visual Studio or other environments, your external program is able to reach in and access internal functions of the simulation software. So as I mentioned, internal scripting appears self-contained, and it appears that you've got very powerful program, but really it provides no fundamental advantage. There's nothing about running a script from within the software that makes it more powerful. However, there are some big disadvantages to it. One is that as a user, you're forced to learn a whole new programming language. And it might be that it's based on an existing language like Fortran, C, Visual Basic, or something else, but it is still that company's own specifically written scripting language. And it's also going to have their own bugs, for example. So depending on the size of the company writing it, they've got to be not only spending development time making their own scripting language, but they've got to be debugging it and developing it themselves. So that presents a huge task, which is taking the company producing it away from their main product. It's also common for groups to want to present all results, such as graphs and videos, from a common environment. So it makes sense for everybody in the group to focus on knowledge of that environment, and therefore it makes sense for that environment to be what's in control of scripts, so that all data comes back into it in the end for purposes such as plotting. The other is that external scripting means that an expert user is to make dedicated apps, just like you get for devices like your phones and pads. A piece of software can have an app. So you can have various projects that are useful to the entire organization or an entire group being generated by one or two dedicated users who know the software very well and who know how to script for it. And others are then able to make use of that without having to know anything about the simulation software itself. As one example, what you see here is an Excel spreadsheet showing what's called a hallback wiggler. The spreadsheet is set up with 7 input parameters that characterize the Hallback wiggler, giving a rotation of magnetization from one volume to another, and allows you to specify the thicknesses and separations and so on for the device. And when you click the Run button, the program is going to go ahead and create the geometry, solve it, and present results back in Excel without the user having to even watch what happens in the Amperes program. As an example of how this works then, the code that makes up the macro within Excel looks like this. It's Visual Basic code, but in particular it invokes the API that's available within the Amperes program by calling Integrated using IES, and then it invokes functions that are shown in red, such as setting it as a static model, running the solver, and asking to get the value of the magnetic field. When it is done, you see a plot appear within Excel such as this. So we will open up Amperes and Excel just to show this running live. So this is just like you saw in the PowerPoint. When we push the Run button, you can see that it's now taken control of Amperes in the background, and you can see the volumes getting drawn, the solver is running, and then when it's finished, the plot has appeared within Excel. But we also have a model sitting inside of Amperes. So if the user is familiar with Amperes, they can go through and look and see, verify the directions of the magnets, and they can go ahead and do their own analyses for force and plots and so on within the Amperes program. But if this has been set up such that everything the user is likely to know comes back into Excel, then really you don't require the user to have any knowledge of Amperes. They only need to know what a Hallback wiggler is, and they can then use this script in order to sit there and experiment with parameters to get the behavior they're looking for. Another example is a project that was created in Visual Studio, which works as a standalone program. So you can run this electro-insulator design project without having to open Visual Studio, because it's a program that exists on the hard drive. When you open this program, you see a whole bunch of parameters which it specify an insulator, and the things that it does are in some cases parametrizable, but in many cases not. For example, the number of sheds generated is not easy to do parametrically in most environments. So this project provides some code that would enable someone to do a variety of things, like run different scenarios, create a plot after each scenario, save the model for future reference, and acquire a spreadsheet of all the data. So once it is run, you can see an example sitting here of what is generated within the Electro program. And again, if the assumption is that you're using this to quickly generate complex models and variations on models for an expert user, pulling Electro to the forefront might be of interest. But it also may be that keeping Electro hidden in the background is all that's required if, in fact, this program pulls out all the information that a user might need. Another example is doing some optimization. So it's very common to have a design project where you've got a goal and you've only got a very small number of things that are able to be varied. So a hypothetical task here is that you want to shape the poles of a C-core magnet such that you get a uniform field of 500 Gauss along the black line that is shown in the middle of the gap. The initial result, which you can see is affected by the fringing for the model as set up, is giving fields that vary from 450 to 485 Gauss. So one obvious thing is the poles need to pull closer together, but the fringing at the edges is going to prevent you from getting a uniform field. So one can think about how you could tackle this such that you would get the field more uniform as well as closer on average to what you're looking for. And the approach that was taken was to break the pole face up with 6 reference points, each corresponding to a sampling point along the line, and to move those points a little bit based on the value of the field. So if the field at the reference point was too low, then that point will be pulled closer so that the field would rise a little bit higher by the gap being smaller in that region. The spreadsheet that was created simply had a run button that would look at the B fields at each of the reference points and then shift at them. So by clicking and looking, click, look, I was able to watch a plot of the B field on one of these points converge. So it began at a given value. On the first iteration it overshot. Then on the next iteration it came a little low. It oscillated up and down a bit, but ultimately came to 500. And for the 3 points it's shown here, the behavior's a bit different, but all of them approach 500 by the time it was finished. And that then produced the pole face shape that you see here, which is not a simple shape. It actually comes out with a somewhat W or M type of shape, rather than being a simple curve. And the result is that at each of the sampling points, which you can get by running down the center here, the field is extremely close to the target 500 Gauss, but of course the field wiggles around those points. However, the average variation has been reduced a lot, so we are much closer to the design goal of a uniform 500 Gauss field. And of course, exactly 500 Gauss doesn't exist. Any real device will not reach any exact values. So the real consideration for any designer is what is the tolerance that's acceptable. And in this case, if 0.4% was acceptable, then you would be done. If 0.4% wasn't acceptable, you could look at some other things like revising the script so that it wiggled 8 points instead of 6 points, and so on. But there's a good chance that if you need substantially smaller variation, then you would also have to look at freeing up some other parameters in order to get there. So in summary, we've presented a few examples to illustrate the automation of simulation for design purposes, and we did this by parametrics and by scripting. And the parametrics were shown to be very quick and easy to set up, and we did that live because it was so easy to do that, but they may be less efficient to run for various reasons, and they may be too constrained and generate extra work when you need to get the results out of your program and into other programs. The scripting, by contrast, is much more powerful in the end, but you will notice that I didn't attempt to write a script live because of the time that would be taken. So there is more upfront work involved in scripting, but you can make much more powerful tools that are ultimately more useful to a large.
Okay, thank you very much, Doug. Very interesting presentation. We have some questions, and we'll take those now. Doug, you with me?
Yes, I am.
Yeah, okay. The first question I have here is, in addition to MATLAB, is anyone using Hyperformix Workbench? I guess it's now owned by CA, or OpNet, now owned by Riverbed.
Okay. Pardon me. The samples that we provide are of the three types that are shown in this presentation, or I guess two types here, but I mentioned MATLAB as well. So of course we can provide arbitrary samples, and there are so many different programming scripting environments out there that we couldn't hope to keep track of them all. What I can say about what I'm familiar with our users working is, of course, those environments that we've provided templates for, as well as Mathematica. I had someone who basically got our update version a year ago, which included the scripting, and later the same day he said, "This is great, I've already got Mathematica working." What I would say to people is that our interface is a COM interface. So if you want to check the documentation on any kind of programming environment and see if you can make something which attaches in Windows via COM, then we should be able to support it with our scripting. But the environments which we actually provide samples in and test, of course, has to be limited to some representative few. And what I've found is that people who want to do very quick, familiar-feeling things like to work in Excel. People who want to make something reasonably substantial and stand alone work from Visual Studio, and people who just plain prefer MATLAB, and there's a huge number of people out there who love doing everything with MATLAB, of course, like to work with MATLAB. So between those three, it seems people are satisfied that they have a good launching point for whatever they're trying to do.
Okay, great. I have another question here, and that is, can I use the same script to control both integrated programs and some other programs?
Yes, you can, and in fact, that was one of our big motivations for putting scripting into the software, was that people were telling us things like, I control everything I do from one script. I control all my simulation, all my CAD drawing, and that way I'm sure that all the data presented to everything I do is always the same. And it's one reason why an external form of scripting, as compared to built-in scripting, is so much more powerful for people who want to do that, because whether it's, again, from Excel, MATLAB, a custom program they make in Visual Studio, the fact is that they can send out commands through a COM interface to any other programs that accept them. One thing I forgot to mention answering the last question, actually, over Christmas I made something that became a video on our website. So if anybody wants to rummage to our website, go through the support section to the videos, there's an example of SolidWorks interacting with our software through their built-in macro language. So that sample's available for anyone who wants as well. But the thing is, people will in general want to do multiple things with multiple softwares, and the COM interface is a way to enable that, to let them have one central thing that controls everything they're doing in multiple softwares.
Okay, great. And I would just direct everybody's attention to the slide in front of you now. It has Integrated Softs, www.integratedsoft.com.
Yeah, and again, the videos are on the support tab. So go down support and you can find videos.
Okay. Another question I have here is, scripting appears to be a powerful tool. Can you comment on when the cost of setting up a scripting analysis process is warranted?
Yeah, for me, I guess that the cost is basically the cost of time, and time to complete a project is obviously important, but also the cost of how much time people are spending interacting with the software. So this is all, of course, a bit of guesswork on your part, but educated guesswork as you get familiar with doing scripting in any given environment. And of course, I'm talking about our software, but the principles of what I'm talking about here apply kind of across the board. You can script all kinds of things. You can script your web browser through Excel if you ever have a reason to. So when it's warranted for you is when your cost savings is basically that you complete something faster and with fewer hours that somebody is putting in order to accomplish the job. That is hours of personal time. If you've got something that the completion date is low priority, but it's taking up a lot of somebody's time, then that's basically costing you their time. Or on the flip side, if somebody might not be spending a lot of time on something, but you need to bring down the overall time that the software is going to be doing the task. Those are scenarios where the scripting is well worth looking at because, for example, with the parametrics, I point out you can loop through far more scenarios than are necessary, but you can get a lot of confidence. But if that is simply going to take too much time, then you want to do some type of more intelligent optimization. And the scripting, especially let's say with the MATLAB optimization toolbox, lets you reduce the number of scenarios you're analyzing in order to bring down the analysis time frame. But the other thing I think was emphasized throughout the presentation is that building tools that reduce the amount of time that a user sits and works with the software as well.
Okay, great. This next question is, you kind of touched on it in your answer here just now. That is, which is better for optimizing a device, parametrics or scripting?
Yeah, so yeah, as you say, I partly addressed that. So parametrics or scripting, really the parametrics is very easy to set up. That's what I always like to emphasize is if parametrics works, then that's really the way you want to go because it's just like click, 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 and you have something set up and it'll loop through and do all the variations you're interested in. But parametrics, all depending on the environment you're in, are by nature subject to constraints. And those constraints may be too restrictive to let you automatically find out all the things you want to know. So when that's the case, then you need to look at spending more time up front to write some kind of program or script in order to overcome the constraints of the parametrics. Okay, great.
Another question here. If I need help writing my scripts, how much assistance does Integrative provide?
Okay, our general support model is that we work very extensively with people, and we don't really get into things like we bill you for time or anything. For the most part, our experience is that people just want to learn enough to get past some obstacle that they have in their analysis. So long as they're a current customer, we just help people. Now, we're not going to write programs for you, obviously, and our ability to debug long sets of code that you write is very limited, but we will work with you in the scripting in particular to get kind of representative examples of things you want to do accomplished. So if you say, for example, you were trying to make a motor work, then we wouldn't program in drawing the entire motor for you, but we would help put together a framework of all the elements that you want to get working. And again, especially if it's in the three environments that we say we support, the MATLAB, Excel, and Visual Studio.
Okay, great. I think we'll take one more question here. How would you compare the parametric and scripting ways of working with batch or macros?
The terminology is non-standard for all this. So when we start comparing parametric scripting, batch, and macros, even essentially the same operation is often referred to under different words. So, for example, I'm old enough that in the past I used to write DOS batch files. Now, when I started working with Unix, I made Unix shell scripts. A shell script and a DOS batch are virtually the same concept. You're writing out command line types of functions, and you can even throw rudimentary loops and the like around it. So batch and script aren't even necessarily different things if you're talking about different environments, but every program has its own ways of using these terms. So in our software, what we call a batch is actually a way of pre-recording, and I decided not to touch on it in this presentation because I didn't think it really added anything. But lots of software enables you to say, if I want to play something back later, so for example, if I want to build models, set them up, get them ready to analyze, but understand that the analysis itself might take some time, I can record a batch that'll open something, tell it to solve, tell it to make a certain number of plots and other calculations, forces and torques and the like, and to save the results somewhere, record another batch to do another one, and so on, and I can then play that back later. And the nice thing about that kind of batch, which is also called macros in some environments, is that I'm essentially making a script, but a very rudimentary script. It's not something I would want to sit there and write out by hand, but it is something which is very useful because rather than learning how to write a script with the API, all I'm doing is using the software itself to pre-record commands to play back later. And sometimes that's very convenient because, for example, over the weekend, if I want to solve 10 different models and produce 10 different plots and so on out of them, I would need to keep coming in and doing that if it wasn't for something like a batch utility. Or I would need to sit there and write out a script which would do it. And simply recording something like a batch or macro is very convenient for that sort of thing.
Okay, great. Thank you very much, Doug. Ladies and gentlemen, we'll wrap it up there. As I indicated earlier, this session will be archived in about 24 hours and can be found on www.spectrum.ieee.org/webinar. Once the archived webinar is available, a notification email will be sent to all the registrants. I'd like to thank our presenter today for making this such an informative hour, our sponsor, and thank you, our audience, for participating in today's session. We hope you found today's event valuable, and will return for future IEEE Spectrum webcasts. Thank you.